Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. If you missed our last show, and if you did, you definitely want to go check it out because it was a great conversation. But if you missed that show, you missed the first of the many exciting updates we have for you this summer. Last time we announced TWiML's third birthday and our 5 millionth download, which happened right around the same time. To help us celebrate this occasion and to request your commemorative TWiML birthday sticker, visit twimlai.com/birthday3. This week, we're continuing the action by kicking off Volume 2 of our AI Platform series. You recall that last fall, we brought you AI Platforms Volume 1, featuring conversations with platform builders from Facebook, Airbnb, LinkedIn, OpenAI, Shell, and Comcast. This series turned out to be one of our most popular series of shows ever, and over 1,000 of you downloaded our first ebook on machine learning platforms, Kubernetes for machine learning, deep learning, and AI. Well, we'll be back at it over the next few weeks, sharing more experiences from teams working to scale and industrialize data science and machine learning at their companies. And we've got even more in store on this topic, so if it's an area you're interested in, be sure to stay tuned. You can follow along with the series at twimlai.com/AI Platforms2 and by following us on Twitter at @SamCharrington and @TWiMLAI. Before we dive in, I'd like to send a giant thanks to our friends over at SigOpt. They've been huge supporters of my work in this area, and I'm really excited to have them as a sponsor of this series of shows on machine learning and AI platforms. If you don't know SigOpt, I spoke with their CEO, Scott Clark, back on show number 50. Their software is used by enterprise teams to standardize and scale machine learning, experimentation, and optimization across any combination of modeling frameworks, libraries, computing infrastructure, and environment. Teams like 2 Sigma, who we'll hear from later in this series, rely on SigOpt software to realize better modeling results much faster than previously possible. Of course, to fully grasp the potential of a tool like SigOpt, it's best to try it yourself. That's why SigOpt is offering you, the TWiML community, an exclusive opportunity to try their product on some of your toughest modeling problems for free. To take advantage of this offer, visit twimlai.com/SigOpt. All right, everyone. I am here with Adrien Gaidon. Adrien is a machine learning lead at Toyota Research Institute. Adrien, welcome to This Week in Machine Learning and AI.
I'm super happy to be here. Thank you for inviting, Sam.
So we are here in Las Vegas at the AWS reInvent conference where you gave a talk, and we will dig into the topic of your talk, which was about advancing autonomous vehicle development using distributed deep learning. But before we do that, I'd like to hear a little bit about your background. How did you get into machine learning?
Yeah, absolutely. So I've been doing deep learning and machine learning for more than 10 years now. I was really interested initially in human learning, human psychology, but I also really like computers and building stuff. So machine learning and AI kind of was like a natural match made in heaven. And so I started doing a double major in computer science and math, and at the same time looking into AI more. And then I did an internship at INRIA in the very well-known group from Cordelia Schmidt in computer vision, where I participated to some competitions like the ancestors of ImageNet, so Pascal VOC, Visual Object Challenges, which I won in 2008. And then I continued the PhD that was with Microsoft Research and INRIA at a joint center in Paris, where I was working on video understanding, more specifically human action recognition.
Okay.
And after that, I joined XRCE, Xerox Research Center Europe. And you actually interviewed a friend of mine, my former boss, Naila Murray, who's the computer vision team there.
Okay.
Great episode, by the way. And so I joined them as a research scientist and worked in video analysis in general, so started that research effort there. At the same time, deep learning emerged, so that's when I really transitioned from principled convex optimization and kernel methods into the alchemy of deep learning, and never looked back since.
Are we saying alchemy just in celebration of the fact that NeurIPS is next week?
Yeah, that's a good one. And from then on, did a lot of work on tracking and especially domain adaptation. And because we didn't have a lot of data, I had to make my own. So I started looking into simulation a lot, game engines to generate data. And I did a couple of CVPR papers on the topic that were noticed by the industry at large in autonomous driving, which at the time was like really getting into simulation. And that's how I joined TRI. Because they're really dedicated to simulation, very, very large scale. These problems only happen at a large scale. If you have just small needs like robotaxi, etc., you can just label data. But at a very, very large scale, and like Toyota is #1 car maker in the world, 100 million cars on the road today. You need to think about these problems. And that's what gets me excited as a machine learning person, because it's all about generalization. And when you think about worldwide, like Japan, Australia, US, everywhere, it has to work. And that's what's really cool, because you both have to invent new things in the research, but you also have to make it work. And you get to touch on all these things. So that's how I got into it. And I got really hooked in the robotic space in general and autonomous driving in particular, because it's such a great application for machine learning.
Okay. Before we get too deep into what you spoke about here, what's the focus at TRI in general, and then your focus there?
Yeah, absolutely. So TRI was created almost like 3 years ago now. It's basically a separate company that was created by Toyota with $1 billion funding initially, and we got $2.8 billion more and spin off a new company called TRI AD Advanced Development recently. Our focus is really, like, we're a robotics company, and our focus is really about autonomous driving, home robots, and we also do some material science research for designing better batteries and things like this. But most of our efforts is really in driving. And the team I lead in machine learning is really about research for autonomous driving. We do also things for robotics a little bit, because from our perspective, a car is a robot. It's a sensory motor loop, essentially. You have perception, prediction, planning, decision, action, and these feedback loops from the real world, which is what's exciting. It's a physical system. And TRI really has a mission to improve quality of life in general. I know it sounds very Silicon Valley, but in that case, it's actually true, because we have already hundreds of millions of users. And so the goal is, one is a project called Guardian, which is to make a car that can't crash. So it's the ultimate driver assistance system. Another one is Chauffeur, which is the real autonomous car, like not the ones we're talking about today, but the long term, the long game, which is real autonomy, like these cars that can drive themselves completely autonomously everywhere all the time, which obviously is not going to happen tomorrow.
We talk a lot about that one today.
Yeah. So this is, but it depends on the product, right? What people think, and here Toyota is thinking really about the long-term thing. Mm-hmm. The cool thing is that these two, Guardian and Chauffeur, in terms of the machine learning side of things, they have a huge intersection. Mm-hmm. You still need semantic segmentation, object detection, tracking. A lot of the algorithms that we're talking about in computer vision are actually completely in common, almost completely in common. So from the perspective of my research, I don't make a difference necessarily between these products, because most of the research I do is very well aligned with those purposes. And then we also do home robotics. So we have like really, really good teams there, ex-NASA, JPL, etc., where they work on mobile manipulation platforms, so that to assist the elderly for home care and these kind of things. So,
and does Toyota have products in market in these in the home robotic space?
So actually, Toyota manufactures a robot that's called the HSR, the Human Support Robot.
Okay.
That was, I think, the official platform for the RoboCup recently. So Toyota is really big on robotics.
RoboCup. I was thinking RoboCop. Wait.
RoboCup with a U. Pardon my French.
Nice.
So the goal is basically, how do we transform Toyota into a robotics company?
Yeah.
They have this amazing like industrial robotics side, of course, but like really, what is the future of cars? And it's going to be robo-cars, but it's also going to be robots beyond cars. And also how they become a software company and actually a machine learning company. That's really what's exciting. Because it's at this scale of a company that they want to change. And the CEO of Toyota was really talking about, like, the song that Andy Jassy is talking about, his keynote, the Clash song. If we don't do it, it's not good. And if we do it, we have to do it right. And right. So that's what's really exciting.
Tell me a little bit about the key message of your talk here at reInvent.
So here, what we wanted to talk about was how you can do a distributed deep learning infrastructure in the cloud that actually scales really well and is highly performant. So when we started this thing, when I took over the team a bit more than a year and a half ago, TRI were really well funded, as I mentioned. So I had dollar signs in my eyes, and I was like, all right, I'm gonna buy so many GPUs. I'm gonna splurge. And we had a server room, we had everything there. And then actually it was still, even if you have the money, even if you have the means at your disposal, it's still fairly slow to ramp up. And we had Mike Garrison, which was doing the talk with me, which is our lead of infrastructure engineering, was telling me, hey, what about Amazon? I was like, they have K80s, they have old GPUs, it's slow, etc. But keeping an open mind, we tried a couple of things. And we got in touch with the AWS folks, and we did a lot of infrastructure work to really make it work. First single node, then multi-node, and using PyTorch. So we're a PyTorch shop. We used to be an anything shop, and then a TensorFlow shop, and we really switched to PyTorch full time a year ago or something. And the talk was really about this kind of journey through which we went from you have an on-prem compute and you can do stuff to really, really large-scale distributed deep learning in the cloud that's efficient. And efficiency is really the key here. And in driving in particular, there's one thing that is very different from, let's say, normal machine learning that you would see at NIPS or CPR, which is we care about small networks that operate at a high resolution. And there's two reasons for that. One is that they need to be small because even if you can compress them, quantize them, and all these kind of things that we know we can make them more efficient, still you need a smaller model initially to fit in computational budget that we have in the car because safety critical. So you have to have really efficient models. And the second thing is you need very high resolution because times equals space. So I was talking in my talk about these weird equations. I was talking about lean deep learning. So you want fast turnaround time and these kind of stuff. We want to create some kind of Toyota production system of deep learning in a sense. So that we can iterate really quickly from idea to model to validation and go back to the drawing board because it's research. This idea of very high resolution is part of one of our constraints that we have to deal with because we want to predict things from far. And so seeing far is when you read the California Handbook of Drivers, it tells you have to look far in the distance to look far into the future. And so resolution is kind of a key thing. It's actually.
And we're talking literally camera resolution?
Camera resolution, yeah. Mm-hmm. And specifically for the computer vision models that we're using. Mm-hmm. And so that means that the compute workload is kind of different because you have small models and very high resolution. So in terms of data flow, operations, time you spend in this metrics multiplies, and all these kind of things, it's very different. So we had
You can't downsample or crop everything to 224?
No, or sci-fi resolution doesn't cut it for us, sadly. No, it doesn't. And so we had to, if you use the standard tools like the data parallel or distributed data parallel from PyTorch, which are amazing at ImageNet and these kind of stuff, they didn't scale for us. And so we had to rewrite a couple of things, and that's what we talked about.
Okay, so let's walk through that journey. So you mentioned that one of the first steps was you kind of had to build up the infrastructure at a node level from scratch. Was that where it started, or were there steps before?
Yeah, no. So we started. So that's the cool thing about TRI is that we're fairly young and we're small, and so there's no technical debt because there was nothing when I started, right? And that was super cool because I'm as a research scientist, I was mostly use this, use that. All right, it's there. Use Slurm because it's this way. I use that's a file system. It's there. Okay. And here was really just sky's the limit, what you should do. And so we really got the opportunity to use the best, partner with the best. So we work directly with a lot of different partners. And then we really created the thing from scratch. And first single node because it was really easy and did all kinds of tricks. Now you have some machines that are monster machines, with 700 gigs of RAM. And so you can scale quite well, but up to a point. And so that's when we started to switch to using distributed file systems. So we did a BGFS-based distributed file system.
Before we leave that initial node, I thought I heard you say earlier that it was difficult and you had to go through a lot of steps to get on that first node up and running. But you just said it was really easy. Assuming that means relative to a full distributed kind of.
So it's this.
What's the? I'm kind of curious about the pain points that you had to go through just to get this up and running, and also the extent to which there's still pain points, or are there other things that have kind of wiped that all away?
Yeah, okay. The first one is this space, right? So the first one is because of the scale of the data we have, you cannot, so for a lot of like, let's say debug experiments or research experiments on small data sets, you can fit them on the RAM, and you should do that because that's just like the best bang for your buck. But when you have large data sets, then that becomes much more complicated. And so we first switched from the RAM disks to EBS volumes or more EFS, or we tried everything. But for like these kind of like this high resolution small networks, to not be network bound, right? To not have this GPU starvation problem where your average utilization of the GPU is like 15% or something ridiculous. And these machines are expensive, so you want to bump that to 90% or above. That's what we had to actually, even before we started really doing distributed computations, using a distributed file system enabled us to really download the data once and not every time you set up a machine. Because if you auto-provision machines and you have to download data from S3 every time you start a machine, then you're saying like, oh, I have this idea. Let's wait 2 hours before I can just like press play, right? So that was a big pain point for research, to have this fast turnaround time. So the distributed file system was something that was very useful at the single node level, and of course scaled to the multi-node. So we did it two birds with one stone.
And so where did you end up with that?
We used the BGFS as a file system, and we're going to look at Lustre, like these announcements that were made recently. That's very interesting. Another pain point that we had was...
And so the BGFS, you're managing it yourself. You just deploying it on a node in your AMI or whatever.
Yeah, so we have like a set of instances that serve that file system that is then mounted on these instances. And we have some infrastructure as code to just like spin this off, like all configured and ready. There's something around containers. So we were baking stuff a lot into the AMI, into the machines themselves. That way when they're started, you're just there directly, because not everybody was familiar with a Docker. But we picked up Docker too, because there's obvious reproducibility benefits. And when you hack a lot of things quickly at the beginning of a research project, having this kind of Docker file where people can reproduce your environment and not just your experiments, that's actually extremely helpful for collaboration in the team. So
it also ties back to that agility and being able to move quickly as opposed to booting up a whole machine.
Yes. And our IT folks were so happy because it's not like, yes, this doesn't work. Yeah, but because you apt-get installed something that wrecked the system. And that's, of course, so DevOps. So really embracing DevOps, even for researchers, actually was quite powerful, because you can only do the research that, the mastery of the tools is really important to empower you to do research beyond, just Python, Jupyter Notebook, let's say. It's an awesome tool, but if you want to go beyond, you need to master other tools. And that's what we've been doing. It's a journey through engineering, craftsmanship, as much as deep learning research.
Does when you talk about kind of applying DevOps in this world, to what degree, in your experience, does it apply directly, or are there gaps, or it only takes you so far, or you have to modify the way you think about it? And I realize that I'm saying that as if DevOps is this well-defined thing. But
I think it's a good question. I think there's like two ways to, like, let's say there's two extremes, right? There's the extreme of you do everything yourself, and there's the extreme of you just use blindly something that someone does for you. And in that space of all the grad students in the world in machine learning, they spend a considerable amount of time configuring their environment. That's a skill we developed during our PhDs. And Docker and these kind of things, if you don't become an IT guy or a DevOps guy, but just learn from the best there, and they do some of the things like around security, and that's really important for data that we have that I don't know. I don't have an inkling, but they exposed us to AWS services. They exposed us to some Docker stuff. So I'm not an AWS expert. I'm not a Docker expert. I'm not a Kubernetes expert. But knowing a little bit of that empowers you to try more bold research ideas and actually debug. And when you care about the performance of your model, not just in terms of its accuracy, but its speed, having this knowledge enables you to do research much faster, actually, which is counterintuitive a little bit. But again, when you're beyond MNIST, that's what it takes.
Right. You started out doing a lot of this yourself meaning like within, as a community of research scientists. It sounds like you were presenting with an infrastructure person. So now you've got kind of, professional support. Yeah,
we do work really tightly with them. My team is probably 30% engineers.
Okay.
And it's really, I think it's really good for research teams to have this mix of really scientists and engineers. And because, again, as I said, the lines are blurred at large scale research, and you need these two skills. And obviously also like all the DevOps and infrastructure engineering teams. So the collaborative spirit at TRI is really, really good. Like, because we're small, we're very tightly knit. And because there was no technical depth, we're building everything together. And really nothing that the infrastructure engineering built was done in isolation without consulting us. So that's why we have a system that works really smoothly, because all the concerns were shared and addressed at the same time from all the pieces of the puzzle. So it's really nice to have that like kick-ass modern infrastructure built around you somehow and with you.
Yeah. And so did that infrastructure engineering team and support, was that always there, or did that come at a certain point after you'd built some things?
Yeah, it's a fairly recent addition. So it started kind of organically, and then you had some people that were there, and it started to be formalized only recently as we scaled up and where that need became much more obvious. So yeah.
And is that infrastructure team primarily responsible for, like, where's kind of the line that how far up the stack did they go? Are they worrying about like tools and frameworks and software platforms, or is it primarily, infrastructure and, network and disk and file systems and connections to the cloud and all of that stuff?
So I would say the latter. So I think the lines are blurry, but you need this single responsibility principle, that applies well for software. It also applies for organization. There's this Conway's law that says that software organization writes software that is architected in a way that reflects the organization, right? And so I think it's really good if you have like clear responsibilities, but also the lines are a bit blurred, because that means that you get a system that is flexible. But you need these kind of responsibilities too. So there's some separation. And in my team in machine learning research, and we are the ones that made the decision to switch to PITorch, for instance. And the way we did that is that, for instance, I re-implemented YOLO myself a year and a half ago in all the different deep learning frameworks. And it was after doing that, like, object detection is really nice because it's a structured prediction problem that's shoehorned into a classification one. And so it breaks the APIs that most frameworks support, like from the get-go. And so if you use that, you're stretching a little bit the capabilities of the network in terms of their the framework in terms of their APIs. And so re-implementing YOLO in all these different frameworks made it clear that as a research scientist, I value flexibility, and PyTorch had the flexibility. Chainer is also very good. There's other alternatives, but debugging and extra. So at certain levels, like, that's why I said, like, research scientists were making engineering decisions, because choosing PyTorch is something that we wanted to make as a research scientist group. And for the reason of the particular research we're doing. So for instance, one of the things we're doing is we did a paper recently called Super Depth, which is a paper about predicting the depth of a scene from a single image. And so we use a self-supervised method where we use geometry as supervision instead of using labels, because for that you can't label. And this is again another example where we use super resolution. So this idea of high resolution is actually important also for accuracy. If you super resolve the images, this helps you predict better depth maps. That was one of the key findings that we made in the paper. And so all that is also enabled because of the choices we made on the software side and PyTorch and all these kind of things, and also around the community that there's around it. So that enables us to really move fast and stand on the shoulder of giants.
So I talked to different organizations that have differing opinions on, how opinionated to be for their organizations. It sounds like you're of the mind to kind of standardize on, in this case, on PyTorch at TRI, as opposed to other places. We're going to build a kind of a framework, a platform, and it's going to be able to support whatever the research scientist or engineer wants to use. Talk me through a little bit the way you think about that.
I think about it in almost mathematical terms. It's the Biasvariance tradeoff. And if you have small bias, right? And if you have like a high variance, and you're really favoring exploration, for these kind of stuff, you need a lot of people that are willing to support you, right? So if you say, oh yeah, Slurm and Kubernetes and PyTorch and TensorFlow and everything, and the little framework that random guy made on his own free time,
Right.
Then so first of all, like, what is actually your business? Like, is it making that infrastructure? And no, for us, it's not. For us, it's making awesome robots, awesome machine learning. So I clearly err more in the bias area, but it's this idea of a little bit of map reduce, right? Exploration exploitation trade-off. With first you have high variance, and for a little while you go wild, you explore, and you're maybe not bound by.
You implement YOLO in every framework.
Exactly, something like this, right? But then at some point you need to make a decision, right? Because that's not sustainable, and you want to move fast in a clearly identified direction. Once you have identified that direction, and you never have enough data to prove that you're right. So at some point you have to have express leadership and just go with it, and then you go for it. And of course you keep an open mind, because then there's the next phase of exploration, because you're right for only a short amount of time in this field of deep learning.
Did we take a diversion on kind of the path that you laid out in the present?
Oh yeah.
We get kind of we take a turn at step one.
We got beautifully sidetracked, but in a wonderful direction. So we were single nodes, everything in the RAM, and then moved to try the existing storage solutions, then moved to more distributed file system. And once we had this, because it's an in-memory distributed file system, we didn't have GPU starvation anymore. But then our training was slow because we were limited to a single machine. Mm-hmm. And then P3 instances happened, so we started to use V100 GPUs, much better. That required also tuning the storage again to avoid GPU starvation. And then we, again, augmented to go into multi-node. And with the distributed file system, that at least the data was easily accessible from all the different nodes. And then that's when we started to hit the limitations of distributed PyTorch, which was very recent at the time.
But before we jump to distributed, I'm curious about you've got some, I guess, quote unquote hyperparameters, like the virtual CPUs, or, the machine configuration parameters. Yeah. Like, are there kind of universal rules of thumb for that kind of thing that you figured out, or do you experiment with it a lot? Is it job dependent a lot? Are you overly focused on economic optimization? Like, how do you work through all that stuff?
So we optimize for time. We don't optimize for cost yet.
Okay, that one was easy.
So that was easy. We haven't. So that's more again the job of the infrastructure engineering people.
So does that mean you just get the biggest one with the best GPU and?
You got it. Okay. Exactly. That's exactly it. So, and also because our workloads, it was obvious that was the only thing to do.
Okay.
So go big or go home. That's basically what we did. Yeah. So for a single machine, we just tried to scale as much as possible on a single machine, and that meant these big instances. We're psyched to use soon the new ones that were announced that are even bigger. So actually, that's feedback that we directly gave AWS. It's quite cool to see that we give them feedback a year ago, and then keynote was, and we heard you, we did this. And so the biggest instances that they made, that's something that we had asked for, and a couple of other cool stuff. So, but you're still limited on a single machine.
And so when you were at kind of topping out at a single machine, how long were your jobs running for?
So at this stage, it was more in the order of weeks. But that's
what kind of job is this?
So the main one in terms of the most computationally expensive one is semantic segmentation.
Okay.
Because again, it's high resolution, it's very dense, it's dense prediction, and so that was the most computationally expensive job. Another type of job that we do that is also very expensive is imitation learning. So we do a lot of research on end-to-end driving. The main reason is not so much that we believe that it's all you need to do driving, obviously not, but we get a lot of data from actual cars, and so we get a lot of demonstrations. And so there's this really interesting research question that we're working on, which is how much value can you derive from these demonstrations? This is a form of supervision on driving that you want to distill down into your models. And so we do a lot of research there, and that's use all the data is really the question that animates us. How can we use all the data? And because we can't label everything, we're not going the active learning routes and the same thing that everybody else is doing, because obviously we're doing that. But that's not the open research challenge. Everybody knows active learning is a good thing to do when you label things. We're really interested in self-supervised learning. How can we really use all the data by leveraging geometry, for instance? How do we use demonstrations at scale? And so those are the workflows. Because motivated by the research direction we're going in, those were the most intensive ones. And a single machine, these are things that easily take weeks.
Okay. So then that necessitated jumping over to distributed training.
Yes, absolutely.
Did you do that after the decision to go with PyTorch,
Yep.
or did you have to figure that out twice?
No, we had made, so because also we have a lot of, like, we're in Silicon Valley, so it's really nice that there's a lot of dense communication between people, are not afraid to share their plans, where they're going. So we know to some extent where things were going, and we know where we wanted to go. So we also were open about this with different partners, and so we knew that when we were going to hit the distributed wall, we would be ready for it. So we had all those factors were factored in at the decision time, at the first one. So we didn't have to revisit it later. Thankfully.
But you did have to, it sounds like, wait on some PyTorch features to support doing distributed the way you wanted.
Yes, absolutely. So initially we were starting to be a little bit afraid that we would have to either fork or do some like really big upstream contribution to PyTorch too. And as I was mentioning, it's kind of like a niche application from the deep learning era, like high resolution semantic segmentation, for instance, is not something that a lot of people are pursuing. So we were starting to wonder if there was another way than to hit like low in the stack, right? And we did like fairly intense debugging, performance profiling, and which is not easy in the cloud because everything is like in the ether. And what we found actually, and that's kind of like was the interesting end of the debugging journey for the performance optimization, was that in the distributed setting, when we had many machines and a very efficient distributed file system, our epochs, right, our passes over the entire training data became really fast because we had this huge batch sizes, and everything was flowing really well to the GPUs. GPUs were crunching really quickly, and what happened is that there was like huge downtimes. Like there was a bottleneck somewhere, and it turns out that bottleneck, which was hard to find, was in the data loaders. When you do how you do multiple workers that prefetch the data for you in parallel to feed the GPUs, like the super hungry GPUs, like really quickly. And in Python, because you have this global interpreter lock, you have to use processes and not threads to do that. And so it's stuck PyTorch data loaders. It starts workers, which starts multiple processes. And forking, like creating a process, is much more heavy than creating a thread. And when you do this very quickly in a distributed setting, that actually became the bottleneck. So we had to change just the data flow and the way we were doing this prefetching in those queues by having some kind of like always warm queues that were kind of like infinitely producing and then infinitely consuming on the other hand. And we're playing with fire a little bit there because we're creating racing conditions, and so deadlocks can happen. But because
this doesn't sound like this doesn't sound like a plugin or something that's
so this was totally not a plugin.
This
so this was
like,
on top, right? This was something that we were using stock PyTorch, except for the data loaders.
Really?
Except for the data loaders, where we changed the data loaders to something in-house. And that's what I mentioned by this warm producers, infinite, and this racing conditions. And recently we've been playing more and more with Horvad. It's an awesome open source library made by Uber.
And it works with PyTorch?
It works with PyTorch.
I didn't realize that.
TensorFlow and PyTorch. It started with TensorFlow and now it's PyTorch. And actually this provides this great MPI-like interface. And that enables, so it's a little bit less efficient for our niche application, but we have other applications. And so the flexibility that you get with Horvad might be worth the price in performance. So we're considering moving more and more stuff to Horvad.
It sounds like you were able to, you invested a little bit in kind of tweaking PyTorch to make it work, but it kind of caught up and now you've got some solutions that work for you. And so you are able to do distributed training. Like, were you done? Like, pop the champagne and. So
it's interesting. In one way, yes, because there was a lot of internal questions. So like I said, Triara is a robotics company, and one thing you have to understand is that in autonomous driving, roboticists, they do things very differently than the really hardcore deep learning crowd, which is they use to LiDAR sensors, clustering methods, like DARPA challenge stuff that work awesomely well and have like much stronger safety guarantees than what we do in deep learning. And so they're not necessarily very experienced in the deep learning way. And so doing these kind of things also means that like training for weeks to develop an algorithm, that sounds insane. And so here doing this distributed training and showing them internally that, hey, you can do things really quickly in the cloud at scale, and you can tweak your models and develop your algorithms almost as quickly as if you were not doing deep learning. That was kind of like a champagne popping, bottle popping moment where they said, oh, that's super cool. Now we actually are going to run with it. Of course, we're not done on the research side. Now we can basically study what happens when you do self-supervised learning on a lot of videos. What happens if you do imitation learning on really a lot of demonstrations. And actually, we have a paper that we're going to push on arXiv soon, where we really push the boundaries of imitation learning and showed that you can go quite far with like deeper models and more data. It's kind of like a prototypical deep learning story, more data, deeper models. That works really well. And that's only thanks to the infrastructure that we had an awesome intern, Felipe, that could do these experiments thanks to that. So we're not there, but we're definitely enjoying the fruit of our labor.
Nice. So the semantic segmentation that before you made it over to distributed was taking weeks. What does it take now typically?
So we can do things in like under 2 hours now.
Oh, wow.
Yeah.
Wow.
That's really fast, yeah.
What does that require in terms of a cluster size?
So we typically run jobs at, I think right now, beyond 8 machines, so beyond 64 GPUs. For a single network, right? We find that we don't need to go beyond that at this stage. So we don't do like a single network on 256 GPUs or something like this, which is most people that do that, at least publicly do that, is just to beat speed records on ImageNet, which is nice. It's not really what we're going for. So for the jobs we do, let's say between 4 and 8 machines, so 32 and 64 GPUs, provides us with like a small turnaround time and good iteration speed for our research.
Is it that the complexity involved in going from 8 to some multiple of 8 isn't is overburdensome? Is it that the value of going from 2 hours to 30 minutes isn't there?
So there's some like more infrastructure problems around like limitation of supply. Like we often joke at TRI we have infinite GPUs because we're in the cloud. Right. But in reality, it's not necessarily there because availability zones, etc. So some things that I don't fully understand. The other thing is also at some point you start to hit algorithmic difficulties. So like for instance, a year ago, people were convinced you couldn't do large batch SGD because you would have generalization performance issues. And that's when Facebook made their, actually, no, it's just a numerical optimization problem. You just got to do the linear scaling rule, this warm up. You have to twiddle a little bit. And then, yes, it generalizes the same way. And that's when you had this explosion of large batch training methods. But still, there's a limit to that, right? And depending on your data sets, depending on your learning algorithm, depending on also the data at hand, right? So the particular generalization gap that you have to overcome, there's a good size of batch size. So beyond there's a limit to how big your batch can be.
Okay. Do you have a single cluster running at a time, or do you spin up multiple clusters and run multiple training jobs kind of constantly all the time? And does that, if that's the case, or even if not really, does that level of change drive you to use something like Kubernetes or some kind of infrastructure? You've mentioned Kubernetes and Slurm and some other things.
Yeah. So right now, the way we do it is we provision clusters on demand by the researchers. So we tend to have a couple of clusters per researcher per project. So that's really nice also because it helps a lot with experimental management. Like babysitting experiments. It's a full-time job when you get closer to the deadline, and having like these separate clusters for the separate workflows for the separate people, that helps with just the cognitive load of where it goes what, etc. And so we didn't feel like, again, my team is like fairly small. We're like 12, 13 people.
Okay.
So we don't need necessarily we do very large experiments, but we don't necessarily do many different experiments. We like probably have 4 or 5 projects at the same time.
Okay.
So no need for like complex scheduling or monitoring or queuing or these kind of things. It's going to get there, and we know it. So that's why we're preparing for that. I have like more an HPC experience, so that's why I favor a bit Slurm. Also because when we started having this discussion, Kubernetes was not supporting GPUs. Now they do. And the only thing I'm a little bit afraid of is adding indirection levels, because again, we care about speed and performance. So this talk that I was mentioning before, we could do that because we were working tightly with the infrastructure engineering team or AWS or NVIDIA. We were actually talking to them directly. And B, we actually knew what was going on under the hood. So we could pop up look under the hood and say, oh yeah, this is wrong, or this is wrong, or this smells funny, can you check this, right? And so if we do too much, add too many layers of indirection, like Kubernetes might be that, I don't know, I'm not sure. I'm a little bit afraid that we lose control and we lose interpretability in a sense. And our models are already hard to interpret, so.
You mentioned in passing the managing experiments, experiment management. Have you built any higher level tooling or infrastructure to help research scientists do that? Or is there something that you're using off the shelf, or is it, Post-it notes and Excel spreadsheets or something?
So we did our fair share of Excel scheduling, of course, do that a little bit. But we had an interesting journey where we initially used TensorBoard, but then TensorBoard didn't scale for us because I had it on disk, and so it just like didn't work. We switched to Wisdom, but Wisdom is a little bit too bare bones. It's very flexible, but there was also other issues there. So we were really starting to think about this, and at the same time, we got in touch with a company, a startup called WNB, Weights and Biases. WNB, Weights and Biases. Yep, Lucas. And they basically, Lucas was just creating his company and basically talked to us and OpenAI and looking for like, what do you guys need? And we really worked really tightly with them. We're happy customers now. And we have this really cool like experiment dashboard, experiment management system, where we can do a lot of visualization of experiments, multi-user, multi-project. It scales really well. So that's what we use today. And so we're really, again, not optimizing for cost, we're optimizing for time.
Right.
And because there's a lot of excitement around machine learning, there's a lot of opportunities to work with great partners. So that's our approach.
When you first mentioned scale there, you were talking about on-disk performance of TensorBoard, but then later when you're talking about it scaling, like how is it doing in terms of, you're not a huge organization, but is it scaling in terms of the number of experiments that you?
So right now we're like probably less than 20 users of that service. Okay. So I can't say about the scaling in the user, but we do a lot of experiments. As you know, researchers, a lot of research is the spaghetti plate strategy, which is you throw it at the wall and you see what sticks. So you have in hyperparameter optimization, all these kind of things means that a single researcher, especially when you have this nice infrastructure in terms of machines and experiments you can run, you're gonna like have a fire hose of metrics you want to visualize, and so that scales really well for that. And again, we're not in the business of making dashboards or these kind of things. So we're really happy to partner or buy whatever is not our core business, which is really about this deep learning models for driving.
And does WNB do the hyperparameter optimization for you?
They
or
have
do you
some
do
service.
Something else?
Yeah, so we do our own stuff there. They have some services there, which we don't use. But I think hyperparameter optimization is like, I'm still on the fence whether this is something internal or something that we can partner with, because there's like typical patterns and typical like algorithms, and I've been a big user of HyperOpt, so you can do Bayesian hyperparameter optimization and these kind of things. And sure, this is like almost standardized, so you could imagine having a service for that instead. But some of these things actually have to hook up really deep into. So it depends on the model and the research project you're doing. So there's a blurred line there. But there's awesome like general purpose algorithms. I think the one that I used the most recently that I really like is Hyperband, which is kind of like a bandit approach that's using the fact that it's our optimization is sequential, so you can restart from a checkpoint and continue and these kind of things. So yeah, on the fence. Some of the things in-house, some of the things black box. It's not. I'm on the fence for this.
And so I'm making an assumption that you don't have to worry about besides from the kind of distributed file system issues that we've talked about, a lot of the kind of traditional enterprise data management, data lakes, data warehouse, hooking into data stores, that stuff. You just need big disks to store stuff.
Yeah. So
right?
we have like we use S3 a lot.
Okay.
And we used to use S3 directly. And so basically what we've been doing is just like what happened with processors. We add layers of cache, and hotter caches, which are getting smaller as they're getting hotter. And we have to like asynchronously, preemptively fill those caches and these kind of things. So it's always the same.
Are these caches like the various S3 features like Glacier and all these?
Yeah, so you can see basically all these different types of storages, right?
Yeah.
As these cache, these are, I call them caches, but it's like metaphorical caches, right? And so S3, we used to use S3 directly as like S3 to GPUs, and that obviously didn't scale. And so we added this different storages and distributed files, EBS, etc.
Distributed file system, all these things.
Yeah.
Okay.
And then you have these prefetching queues that are literally filling the RAM with next to your GPUs, and so you have this ultimate layer of cache, right?
Okay. And then on the back end, do you have to worry about inference and model serving?
So at this moment, the inference is the models we serve are in our robots, right? So that's a big thing, right? Is that the models we serve are the ones that are going to be in the path to actuation of the car. So there we have like amazing driving technology teams that own parts of the stack. Like we have an object perception team, we have a SLAM team, we have a planning and controls team. And these guys, they basically take our models or make their own, and they make them more efficient, fit them in the computational budget that they have, and that's how we serve models. So that's a fairly different model than, let's say, a web-based application.
Yeah. And is that process of getting the models to fit, compression or pruning or what have you? That's still a manual process to a large degree? Is that right?
So to some extent, there is these. It's kind of a little bit weird because there are some ways that are productized a little bit, like there's TensorRT and these kind of things, but it's still more an art than a science. So it doesn't always work. It works for certain types of network, like out of the box, but some it doesn't. And so there you have some, tools or a bag of tricks that are general purpose that you can throw at this, and that you should throw at this definitely, and that our teams are doing. But more upstream on the research side, and my team, what we're doing, you can learn models that are compressible or that are amenable to compression by having some compressibility factor built in. You can have also small models, like as I mentioned, right? And there's more and more research results that show that small models can generalize as well as big models. They just have to train for longer, or you have to change the learning algorithm. And another thing is, one of the big things we're trying to do is how far can we go with multitask learning, right? Because if you can have a shared backbone and squeeze many different things, that's awesome. And the one recent project that we did around panoptic segmentation is basically this. Is basically take semantic segmentation and take instant segmentation, so mask our CNN and these kind of things, and that works really well, but that's extremely slow. I think like mask our CNN is like 150 milliseconds per image or something, and you have to basically reduce those models and merge them together with maybe different heads to make it efficient. And we made a recent paper, it's going to be on archive soon, called TaskNet, for Things and Stuff Consistency Network, where we basically merge them together and have a task consistency, a cross-task consistency, because the main problem with multitask learning is if you just sum the losses, it doesn't necessarily, like they maybe contradict each other. It's a bit like when you're arriving at an intersection, it says turn left or turn right, you don't know, you go in the middle, there's a wall there, not a good idea. So like imagine the gradients might be pushing in orthogonal directions. So one of the key things we did is we actually augmented the objective to have a consistency encouraging objective. And between the stuff classes, like so road, sky, etc. on the semantic segmentation side, and the thing classes on the instance segmentation side. So merging these networks is one way to be more efficient. And that's some of the very recent work that we've been doing.
How have we done in terms of kind of getting a lay of the land of your presentation?
We went way beyond.
Yes.
So excellent.
Nice. Awesome. Any kind of parting thoughts or words?
No, I think we're really excited at TRI to continue this direction of large-scale deep learning in the cloud and tackling this really, really challenging open research questions. So we're continuing to grow very, very fast and excited to be in that space, self-driving robots and with deep learning. So very happy to have been able to talk about it.
Awesome. Well, thanks so much, Adrien. It was awesome to have you on the show.
It was a pleasure.
All right, everyone, that's our show for today. For more information about today's guest or to follow along with our AI Platforms Volume 2 series, visit twimlai.com/AI Platforms 2. Thanks once again to SIGOP for their sponsorship of this series and support of the show. To check out what they're up to and take advantage of their exclusive offer for TWiML listeners, visit twimlai.com/SIGOPT. As always, thanks so much for listening, and catch you next time.